Yes, welcome back to this course on materials and mechanical design. So, in our last class, what we have referred to was the description about the unidirectional composites. We have seen that how we can actually identify the material axis in a unidirectional composites, and regarding that, we have seen that the the direction along the fiber's length is actually referred to as the longitudinal direction, and the directions across the fiber is referred to as the transverse direction T, and then we have the T prime direction, which is perpendicular to L and T both. Our aim happens to be here referring to composite materials as a type of hybrid materials, and we want to actually find out a way to actually know their properties, specifically the modulus of these materials. We already know that the modulus of these materials will depend upon the modulus of the constituents that are there in this composite material, means what is the material of the fibers here and what is the material of the matrix here. Similarly, we may be interested about the physical properties of the resulting composite material, like what we refer to as the density of the composites. It is an important property when we refer to what we call as lightweight designs, where it is a requirement that our designs must be of minimum mass. And moving ahead with that how we can actually predict the density of composites. There are a few assumptions which we need. The basic underlying assumption in this particular property prediction happens to be that it is a two-phase system and there are no voids. So what you have is only two phases. One of the phase is referred to as the fibers and the second phase is referred to as the matrix. And going by that, we can simply write that the total mass of the composites here happens to be the mass of the fiber plus mass of the matrix material. When I divide this whole of the expression by the volume of the composite, I get the expression modified like this, and then going forward I can simply write mc upon vc as rho c, that is mass per unit volume of the composite can be written as the density of composite, and mass of the fiber is then modifiedly written as rho f into Vf. That's again based upon the expression for the density. So I write rho C is equal to rho f Vf upon Vc plus similarly rho m Vm upon Vc, which we then write it as rho C, that is the density of the composite can be written as rho f. Rho f comes here, and then Vf upon Vc is what? We understand that Vf upon Vc is nothing but the volume, the ratio of the volume of the fibers to the total volume of the composite material, which we say is Vf, capital Vf, which we write as the volume fraction of the fibers. And similarly, we get plus rho m, this is here, and then Vm upon Vc is nothing but the volume fraction of the matrix. This expression which I write here is expression also called as the expression used for finding out or predicting the density of composites based upon what we refer to as the rule of mixtures. Keep it in mind that we are actually talking about volume fractions here. In our next slide, we'll see that how we can convert these volume fractions into weight fractions. Sometimes it may be essential for us to know something about the weight fraction also. So, but before moving forward, just note down this expression which we write here as the density of the resulting composite is nothing but given as rho f Vf plus rho m Vm. Going back to my last class, you may have already known that when I set the limits of the density here of fibers and density of the matrix here, we had limits starting somewhere from 500 kilograms per meter cube going up to 22,000 kilogram per meter cube for osmium, and then 500 was for lithium as such, and all the other materials lie almost within this range. So we need to be particular regarding that what can be actually the density of the composite which I make out of by combining two materials. One of them is the fiber material and the second one is the matrix material. Okay. Now going forward, as we said, we want to then convert these volume fractions into mass fractions. So I simply write a simple expression that total volume of the composite happens to be volume of the fiber plus volume of the matrix. When I divide this whole expression by the total mass of the composite, I write the second expression, and then Vc upon mc is nothing but, it can be simply written as 1 upon rho c, because what is rho c is nothing mass per unit volume, mc upon vc. It can be simply written as, now this is vf upon mc, and what is vf? Vf is nothing but mf upon rho f. Similarly, vm can be written as mm upon rho m, that is mass of the matrix, upon rho is the density of the matrix. And we already know that out of this expression, now what is mf by mc? Mf by mc is nothing but the mass of the fiber divided by the ratio of the mass of the fiber to the mass of the composite material, which we write as the mass fraction, mf. And similarly, mm upon mc can be written as mm, that is the mass fraction of the matrix material. So I then modify this expression, and then it can be written as the next expression, which I write as 1 upon rho c is equal to mf upon rho f plus mm upon rho m. So we have seen that lastly we had the volume fraction calculations given to us, and then we can actually convert those volume fractions and then get the mass fraction calculations also if the density of the resulting materials, of the used material, is known to us. Keep it in mind that when I started this discussion, we said that we are having a two-phase system where there are no voids. So what you predict here, rho c will be the theoretical density of the composite, assuming that there are no voids in the system. If there are voids in the system, obviously the resulting density of the experimental value of the density will be slightly, or will be less than the theoretical density which is predicted by this expression. So that we need to take care of in this particular expression here. Okay. Now that was regarding the prediction of the physical properties like density. Now we want to predict some more properties like the modulus. So we need to know that how you predict the modulus of the unidirectional composite, and there are a number of assumptions which we must understand clearly, and we must also understand the significance and the reason that why we are making these assumptions during this basic formulation for predicting the modulus of the unidirectional composites. So the first assumption which we made here is that we are making here is that fibers are uniformly distributed throughout the matrix. So it's not that means the total fibers are actually uniformly distributed in the matrix. There are no matrix rich regions and there are no fiber rich regions. Means whatever is there, it is all uniformly distributed. It may not be true, but we make this assumption because our next analysis will be based upon taking one particular part of the, or say, representative volume element will taking out of our material, and that is why we are saying that volume is representing the whole of the material, and that can only be true if we say that fibers are uniformly distributed throughout the matrix. Okay. The second and very important assumption which is required here is that there is a perfect bonding between the fibers and the matrix. So I will talk about in detail about this assumption in my next discussion, that what is the reason that we are making this assumption here. Similarly, this assumption which I used in my last slide was on density calculation, that matrix is actually free of void. So that's another assumption that we have here. The next assumption, that we'll be analyzing loads to begin with only on directions which are either parallel or normal to the fiber direction. So you may be talking about fiber loading along the L direction or loading along the T direction. And initially the lamina is a stress-free state. There are no residual stresses, which may not be true in many cases, because we understand that the fiber and the matrix, they have different properties. So when they solidify, when they cure, they have different what we call as thermal expansion coefficients also, because of the isothermic reaction that happens in most of the thermosetting resins. We find that there are shrinkage stresses which are normally developed in composite materials, but we are assuming that there are no stresses initially. That means there are no residual stresses. So these are the 5 assumptions which are very important to us, and I will talk in detail about the second assumption in my next slide here. Okay. Then the another assumption which we intend to use is a simple one. We say that both the fiber and the matrix behave like linear elastic materials. That is why the Hooke's law is valid, and we are actually talking about only in the elastic limit. So deformations, whatever are happening, the strains which are produced, they are within the elastic limit. Okay. Now, what we want to do now is we want to predict the longitudinal modulus of the composite material, which I represent here as E subscript L. So we write it as EL. For doing this exercise, we will be making one assumption, which we say is an isostrain assumption, equal strain assumption, which tells me that the strain produced in the composite, that's epsilon C, is equal to epsilon M is equal to epsilon M. It is here that our assumption about what we refer to as perfect bonding between the fiber and the matrix comes into picture. So this is a graphical representation of what I am referring to here. So this is a representative volume element, means I have taken out one fiber and this is the fiber direction. So one direction refers to our L direction here. So we have this fiber which is aligned along this one direction or the L direction, and this is the second direction which we say is the T direction, and we have the fiber here which is encapsulated in the matrix material here. So when I apply a load along the one direction, what we observe is that there is a change in length. So a strain is produced, so the total length of the composite, which was already L before the application of the load, it undergoes a change in length delta L, and that is where what I was referring to, that we are assuming that there is a perfect bonding between the fiber and the matrix. That is the only assumption which is telling me that both of them will get elongated by the same amount. If there is an imperfect bonding, this equal strain assumption will not hold good. The equal strain assumption will not hold good. Then we cannot say that the strain produces the same. So that's where we say the assumption of perfect bond between the fiber and the matrix is essential here, so that we can then take about the same strain in the matrix, fiber, and the composite material. Okay. So moving forward, I will what people have been doing is that they have been analyzing unidirectional composites in the form of a slab model. So what is the meaning of the slab model? So we say that the total composite can be represented theoretically as one slab of matrix, which is the yellow portion here, and then all the fibers combined together is the blue portion. So we say, instead of analyzing them as separate fibers along the length which are distributed here, we say we can simply analyze that all the fibers are here combined together and all the matrix is here in this yellow region, and we say that is called as the slab model of the composite. This longitudinal modulus is also referred to in literature as void modulus, and we move forward with this formulation, and what we further know is that the total force, if you apply a force along the L direction here, this is one is the L direction here, the total force, if I say is P or PC, is equal to the sum of the forces acting on the fiber and the matrix, which simply tells me that total load F or P, whatever we talk about it is, in the longitudinal direction is shared by the fiber and the matrix. So it shall be written as P here, not F. So I simply write PC, total load of the composite, is equal to sum of it is shared by the fiber, PF, and sum of it is shared by the matrix, we say it is PM. I rewrite P as a sigma C AC, similarly PF as sigma F AF, and PM as sigma M AM. Because Hooke's law is valid, that is why I can simply write sigma C as EC epsilon C, and similarly sigma F as EF epsilon F, and similarly sigma F as EM epsilon M. If I divide this whole expression by AC, that is the total area of the composite, resulting composite, I get it as EC epsilon C equal to EF epsilon F, and it is now AF upon AC, similarly AM upon AC. So we already know AF upon AC is equivalent to VF, that is volume fraction of the fibers, and AM upon AC is equivalent to VM, that is volume fraction of the matrix here. So I land with this expression here. In this expression, I understand that we have taken the equal strain assumption, which was telling me that epsilon C is equal to epsilon F is equal to epsilon M. And that is why I can simply write now EC. EC, what is EC? The modulus of the composite material, which has been made by combining a fiber which has a modulus EF and a matrix which has a modulus EM in a particular volume fraction which we write as VF. So I then replace this EC by EL, which simply means that it is the modulus of the composite material in the longitudinal direction, that is along the direction of the fiber. There is nothing but EF VF plus EM VM. So we see here simply that EL is actually dependent upon EF, VF and EM. To get a better understanding of the influence of the stiffness of the fiber material and the stiffness of the matrix material, we rewrite this expression here as EL by EM. So I'm just simply writing this as the ratio of modulus of the composite material along the L direction to that of the matrix material. So if I write EL by EM, this expression gets modified to EF by EM into VF plus 1 minus VF, which can be further rewritten as EL by EM equal to EF by EM minus 1 into VF plus 1. So please have a look at this expression. What we are interested about is the ratio of EL to EM. We kept in mind in our design of composite that we want that the EL, the value of modulus of in the longitudinal direction of the composite, must be higher than the modulus of the matrix material. That's what we say. This EL by EM must be actually greater than 1. If that is so desired, it then depends upon directly the ratio of EF to EM. That is, what is the ratio of the stiffness of the fiber to the stiffness of the matrix, and then the volume fraction, how much fiber you are putting into it. Simply speaking, if you want to have higher values of EL by EM, means I want to reinforce my matrix to a higher value, EF by EM must be high. So higher is the EF by EM value, EL by EM will be high. And second thing is that VF must be also higher, that volume fraction must also be higher. So I simply write this ratio as the gain in stiffness. Gain in stiffness means gain in stiffness of the matrix, because matrix is considered to be a material which is having low stiffness and fiber was a material which is having high stiffness. By combining them I get EL, and that ratio of EL to EM, thus the high stiffness composite to the low stiffness matrix, is what we say is the gain in stiffness. So the gain in stiffness then can be written by this expression. Okay, so this is what I referred to earlier also. The major aim of forming a composite is generally achieved only when the stiffness of the resulting composite is greater than the stiffness of the matrix. So I recall my earlier expression, that is EL by EM is EF by EM minus 1 into VF plus 1. And this equation tells me that the gain in stiffness with respect to the stiffness of the matrix depends upon two parameters. I already told you that the ratio of EF by EM, and the second is the volume fraction of the fiber. So these two parameters decide that what is the gain in stiffness that we will have, which takes me to one more interesting observation here. We are observing here that if I use high stiffness fibers, the gain in stiffness will be higher. So just an example which we can quote here is that when I compare glass fibers with the carbon fibers, so for a constant volume fraction of 10%, when I put 10% glass fibers in my polymer matrix, because glass fibers are less stiffer than the carbon fibers, that is why EL, that is this may provide you EL by EM equal to 3. EL by EM equal to 3, because EF of glass fibers is less as compared to the carbon fibers. But when I for the same volume fraction of 10%, when I replace this with the carbon fibers, the gain in stiffness is almost 10 times. So we understand that this gain in stiffness is proportional. It is actually dependent upon two parameters: the ratio of the stiffness of the fiber which we are using and to that of the matrix. So using a stiffer fiber will give me a better gain in the resulting stiffness, gain in stiffness of the composite material. Okay.